The ninth problem of ours is a pretty interesting problem. We are given that the tangents are drawn to the parabola y square equal to 4ax at the points P and Q, and the inclinations of these tangents to the axis of x are theta 1 and theta 2. If A is the vertex of the parabola and circles are drawn on AP and AQ as diameters, and these circles intersect in R, and AR is inclined at phi to the axis of x, then we need to prove the relation cot theta 1 plus cot theta 2 is equal to minus 2 tan phi, where theta 1 and theta 2 are the inclinations of the two tangents to the axis of x, and phi is the inclination of AR to the axis of x. Now this problem appears to be very large problem, and you may think that it is a difficult problem, but again I would suggest that if you apply the simple basic principles and the key concepts of the parabola, then we would be able to do this problem within a few minutes. First of all, it is given that tangent at P is having an inclination of theta 1, and we know that on any point a t1 square comma 2a t1, let's say this point is P, we know that at any of this point, if a tangent is made, then the slope of tangent is 1 upon t1. So we can write for point P, whose inclination is theta 1 to the axis of x, that tan theta 1 is equal to 1 upon t1, where a t1 square comma 2a t1 are the coordinates of point P at which the first tangent is made, which gives cot theta 1 is equal to t1. Now if a t2 square comma 2a t2 are the coordinates of point Q, then in the similar fashion cot theta 2 is equal to t2. This is a first and this is a second relation. Now it is given, then circles on AP and AQ as the diameters have been drawn, where A is the vertex of the parabola, and we know that if the extremities of diameters are given as x1 comma y1 and x2 comma y2, then the equation of circle can be written as x minus x1 into x minus x2 plus y minus y1 into y minus y2 equals 0. Hence circle on AP as diameter can be written as x minus a t1 square into x minus 0, since A is the vertex, it is 0 comma 0, into x plus y minus 2a t1 into y minus 0, that is y, equals 0. And similarly on AQ as diameter, just replacing t1 by t2, we'll get the equation of circle with t2 as diameter, or rather AQ as diameter. Now it has been given that these two circles intersect in R, and we know that one of the point of intersection is A, definitely. So the common points of intersection are A and R. So the equation of common chord can be found out by subtracting the two circles, that is S1 minus S2 is equal to 0. The first circle is x square plus y square minus x a t1 square minus 2a y t1 equals 0, and the second circle is x square plus y square minus x a t2 square minus 2a y t2 equals 0. On subtracting the two circles, we get the common chord equation as minus ax times t1 square minus t2 square minus 2ay t1 minus t2 equals 0. This a and a can be cancelled, t1 minus t2 can be cancelled, so we get x times, this is t2 square, t1 plus t2 plus 2y equals 0. This common chord is the equation of line AR, and the inclination of this line AR with the axis of x has been given to be equal to phi. So we can write tan phi is equal to the slope of this line, which is equal to minus t1 plus t2 by 2. On putting the value of T1 as cot theta 1, value of T2 as cot theta 2, we can get the desired relation 2 tan phi or minus 2 tan phi is equal to T1 plus T2, which is cot theta 1 plus cot theta 2. Hence we have seen that I have not used any special formula, any special result for solving this problem. We just use simple basic key concepts of parabola to prove the desired result as minus 2 tan phi is equal to cot theta 1 plus cot theta